There are two types of IP addresses. One is private IP, and then we have public IP. As the name says, private IPs are meant to be kept private, and public IPs can be used publicly, which means private IPs can be used internally in a lab environment or in an office environment, but public IPs can be used in a public infrastructure. When you are going out to the internet, you need to use public IPs. There is a fixed range for private IPs that can be used by anyone, but then for public IPs, you need to purchase them from the authorities. One example of a private IP is 192.168.1.1. An example of a public IP is 8.8.8.8. When you connect to any network, you always get assigned a private IP. So when you're at home, you connect to your Wi-Fi. The Wi-Fi assigns your machine a private IP. But then when you try to go out from that computer, then your router changes that private IP into a public IP, because over the internet, your private IP is not routable. It cannot go out, but public IP can. There are quite a few number systems. We'll be discussing here about decimal, binary, and hexadecimal. So decimal number system has total 10 numbers starting from 0 to 9. Binary, pi means 2, so it has two numbers here, 0 and 1. Hexadecimal, so hexa is 6 and deci is 10. So there are total 10 numbers in this number system starting from 0 to 9, and then we have from A to F. These numbers, they make hexadecimal. Anything that we regularly use, that is a decimal number system. For example, you write number 9, it's in decimal number system. The binary number systems are only ones and zeros, so any number if you need to write, you will only use these two numbers to write that. For example, if I need to write 5, so I cannot write 5 here. That would be wrong. That's the decimal number system. I need to write 5 in binary, so I need to convert that into a binary number, which will just turn out to be a combination of some ones and zeros only. So how to convert a decimal number into binary? To do that, you'll need to remember this small formula here. So you'll start writing these numbers from your right hand side, 1, 2, 4, 8, right? And this way you can keep on going. So it's multiple of 2, 1 into 2, 2 to 4, 4 to 8, 8 to 16, 16, 32, 32 to 64. The task was to write number 5 in binary. Which numbers will you add to get number 5? So 4 and 1. So the numbers that you're going to use, keep those bits high and everything remains low. The number you get, the binary for 5 is 0101. Similarly, if you need to get a binary for number 10, so 10 is 8 plus 2 and everything else remains 0. So the binary for 10 is 1010. Okay. Let's say I need a binary for number 15, and that would be 8421. If you add all of them, you get number 15. So the binary for 15 is 4 times 1. This is how you convert a decimal number into binary. If you need to convert a higher number, because the maximum range that you get from 4 bits is number 15, if you want to convert a bigger number into binary, then you'll need to extend this formula, 8 to 16, 32, 64, 128, like that. So if I need to find a binary for 224, then that would be 128 plus 64, that's 192, and then plus 32. Everything else remains 0. So the binary for 224 is 111, 0, 0, 0, 0, 0. So we have total 8 bits here. So now we'll see how to convert a decimal number into hexadecimal, which is not very frequently used, but it's just that you should know. Let's take an example for a conversion. Let's say we have a number 952, and this needs to be converted to hexadecimal. So first you need to divide this number by 16. When we divide this number by 16, we get, so that's 60, and then there is a remainder of 2. Then you'll need to again divide this number by 16 because there are total 16 numbers. So then you get 3, 16, 3, 48, and then we have a remainder of 12. And again, you need to divide this number by 16. So that will leave the quotient as 0 and remainder as 3. So if we divide this number again by 16, now we get 0 and the remainder is 3. Right? So now we'll need to take the remainders in the reverse order. So first of all, we'll take 3, then we have 12, then we have 2. And now convert them to their hexadecimal value. So 3 in hexadecimal is 3, 12 in hexadecimal is, so we have 0 to 9, and then we have 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 F. So here we have number 12, 12 becomes C. So we have 3C2. That is the hexadecimal conversion of base 16 for a number 952 in base 10. So base 10 means it's a decimal number system. Base 16 means it's an hexadecimal number system. Class of IP addresses. The IP addresses are divided into two types of classes. We have classful and classless. So first we'll talk about classful IPs. The classful IPs are further divided into 5 classes: class A, class B, class C, class D, and class E. These are the most used classes of IP addresses, A, B, and C. Now, how do you identify which IP address belongs to which class? So just by looking at the IP. And to understand that, we need to take a step back and understand the format of an IP address. An IP address is a 32-bit number, 4 octets separated by dot. So this is octet 1 dot octet 2 dot octet 3 dot octet 4. An IP address has 4 octets. Total size of the IP is 32-bit, which means each octet is 8 bits. As you know that 8 bits equals 1 byte. So each octet size is 8 bit here. So that makes 8 into 4, 32 bit. The total size of the IP is 32 bits. Now, how to identify the class of the IP? You will do that just by looking at the first octet of the IP address. So if the first octet ranges between 0 to 127, that IP address belongs to class A. The first octet range for any IP is from 128 to 191. That IP address belongs to class B. If the first octet range is from 192 to 223, that belongs to class C. If the first octet range is from 224 to 239, then that IP address belongs to class E. And if the first IP address range and if the first octet range is from 240 to 255, that IP address belongs to class E. So this is something that you will need to remember. If the first octet of an IP address falls in this range, then you will know that that IP address belongs to class A, B, C, or D, or E. So class D and E are not that frequently used, especially class E has been totally reserved for research purpose, but class D is still used for routing protocols. You will be mostly dealing with class A, B, and C. Now we know about the classes of IPs. Next thing we'll learn is what are the private ranges for each class. So each class has remember there are two types of IPs, private IP and public IP. Private IPs can be used by anyone. To use a public IP, you will need to purchase them. Private IPs are used internally and public IPs make sense over the internet. We need to understand what are the private IPs so that we can use them. In each class, there is a fixed range of private IPs that you can use. For class A, that ranges from 10.0.0.0 to 10.255.255.255. For class B, we have this range starting from 172.16.0.0 till 172.31.255.255. class C, it's 192.168.0.0 till 192.168.255.255. So now you know that why each octet is going up to 255, because an IP address is a 32-bit number separated by dot, right? And we have 4 octets here. Each octet is 8-bit. If you write 8 bits in binary, so let's write that formula here: 1, 2, 4, 8, 16, 32, 64, 128. I think these are 8 numbers now. And in binary, if all the 8 bits are high, then what number do we get? That is the number we get. These are total 8 bits now. If you add all these numbers, it will turn out to be 255. So that is the maximum number that can come in one octet. It ranges between 0 to 255. And start from 0, all these bits can be 0, or all these bits can be 1. If they are all 0, then the number is 0. And if all the bits are high, then you get a number 255. Then we have subnet mask. The subnet mask tells what part of your IP address is network ID and what part is host ID. So for class A, B, and C, there are fixed ranges of subnet mask. For class A, the subnet mask is 255.0.0. It means first 8 are network bits and then everything else is host bit. The short notation for the subnet mask is /8. Subnet mask for class B IPs, it's 255.255.0.0, which means class B has the first 16 bits as the network bit, and then we have host bits /16. For class C, the subnet mask is 255.255.255.0/24, which means there are 24 network bits. 8 bits, 8 bits, 8 bits, that turns out to be 24. Similarly, 8 bits plus 8, 16 bits. So these are network bits, number of network bits. Subnet mask is number of network bits. The next concept is subnetting. Subnetting is dividing a bigger network into smaller networks, which brings us to another discussion about the class of IPs. So now subnetting makes the classful IPs into classless. The differentiator here will be the subnet mask. For classful IPs, we had a fixed range of subnet mask. If it was class A, then the subnet mask will be /8. If it was class B, then subnet mask would be /16. And for class C, the subnet mask is /24. So these are some well-known subnet masks that you need to remember. /24, /16, and /8. That means there are 8 network bits, there are 16 network bits, and 24 network bits. When there are 24 network bits high, then the subnet mask will become 255.255.255.0. Similarly, for /16, it's 255.255.0.0, and for /8, 255.0.0.0. These are the well-known subnet masks that you must remember in order to understand subnetting. Okay. With that being said, let's jump into subnetting. So subnetting is dividing a network into smaller networks. For example, we have a network. So to understand the subnetting, we'll start with an example. So let's take an example of 10.0.0.0/27. So when you go into classless, the subnet mask can be anything. So you'll need to figure out how many bits of this IP are network and the remaining are host bits. So as you know that this subnet mask is known as network bits, right? So first thing you need to do is convert this into a subnet mask. /27 is close to which number here? 8, 16, or 24? It's closer to 24. We already know the subnet mask for /24. We just need to find the subnet mask for 3. So 24 plus 3 make 27. Since you know the subnet mask for 24, let's just write that. So that's the subnet mask for 24, 255, 255, 255. So 24 network bits are high now, right? We need 3 more bits. So let's write that formula again. 1, 2, 4, 8, 16, 32, 64, 128. So 24 bits are already high. We need to set 3 more bits high. So we'll set 3 bits high from the left hand side. So 1, 2, and 3. And everything else remains 0. If you add these three numbers, it will turn out to be, so 128 plus 64 is 192 plus 32, 224. That is the subnet mask for /27. Next thing is we need to find wildcard mask. So wildcard mask is, it tells you what will be the range for the network. Like when does the new network start? The wildcard mask is exactly opposite of the subnet mask. What you need to do is subtract each octet of the subnet mask from 255. So let's take 255 here and subtract each octet from 255. So 255 minus 255 is 0. 255 minus 255 is 0. 255 minus 255 is 0. So 3 zeros. And then we have 255 minus 224. So that is, that turns out to be 31. So this is the wildcard mask. Using the subnet mask and the given IP address, we can find the network ID. So what you need to do is you need to find the network ID of a network. You will use the given IP and subnet mask. So this is a logical AND. We'll do a logical AND operation between the given IP and the subnet mask, and that will give you the network ID. Let's see how to find out the network ID for this 10.0.0.0. Though it looks very simple that its network ID is going to be 10.0.0.0, but that's not always true. For you, many times the network ID will turn out to be different based on the subnet mask. Alright, so logical AND is to understand the logical AND. So when it comes to logical, we are talking about zeros and ones. So to understand the logical AND operation, you need to remember this table. So think of logical AND as a multiplication. So when you can have with two bits, you can have these many combinations: 0, 0, 0, 1, 1, 0, and 1, 1. So when you perform a logical AND or a multiplication between 0, 0, that turns out to be 0, 0, 0, and 1. So only 1 and 1, when you multiply them, will be 1. If you multiply 1 with 0, that becomes 0. So wherever you have 1, 0, the logical AND operation between those numbers will result into a 0. This is how you do logical AND operation. So when you do a logical AND between the given IP and the subnet mask, you get the network ID. So here, let's say this is a very simple example, but you can also use this in complex examples as well to simplify some part of your conversion. So right now we have 255.224. Right? If you need to perform a logical AND operation here, we'll look at the given IP octet. So we have 10 here, but the subnet mask is 255. 255 means all ones. All the bits in this octet are 1, right? That is how you get 255. So if all these bits are 1, if you look at the logic of logical AND, wherever you have 1, the result is always the other number. So if you have 1 here, then the result is fully dependent on the other number. So now 255 into 10, because 255 is all 1, so we'll get the exact same number, right? And then we have 0, so 0 into anything else becomes 0, 0, and then 0. So the network ID for this particular subnet is 10.0.0.0. Did some cleanup here. The given IP address or given example was 10.0.0/27. First, we figured out that its subnet mask will be 255.255.255.224, and then we calculated the wildcard mask. So to find the wildcard mask, you subtract each octet of a subnet mask from 255. So that turns out to be 0.0.0.31. Then you find the network ID. To find the network ID, you do a logical AND between the given IP and the subnet mask. So when you do that logical AND, it turned out to be 10.0.0.0. So you now have the network ID. Now you need to find the broadcast ID. Broadcast ID is the last IP address of a network. To find the broadcast ID, you use the network ID and then add wildcard mask to it. So this addition will be done in decimals. For example, the network ID here is 10.0.0.0. The wildcard mask is 0.0.0.31. So you add them, you get 10.0.0.31. That is the broadcast ID, which means the last IP of this network. Network ID is the first IP of this network. The network starts here, that's the first IP. The network ends here, that's the last IP of the network. Okay. Now, what will be the next network? So that is just right after this, 10.0.0.32. This is where the next network starts for a /27. Okay. Now in this network, how many IPs do we get? The network that starts at 10.0.0.0 and ends at 10.0.0.31. It looks like it's a very simple calculation, so we got approx 32 IPs. But then wait, you cannot use network ID and broadcast ID as an IP. They cannot be used as a usable IP. So always you'll have to exempt network ID and broadcast ID from the usable IP ranges. So you get 30 usable IPs here. There is a formula that you can use to find out how many usable IPs you get out of a network. For example, if someone asks you how many usable IPs are you going to get in a /27 network, so you use this formula, 2 to the power host bits minus 2. As you know that the subnet mask is network bits, right? Subnet mask is network bits. There are total 32 bits in an IP address. So if 27 are network bits, then how many are host bits? 5. 2 to the power 5 minus 2, which is 32 minus 2, so we get 30. So you get 30 usable IPs. Even if you find the difference between broadcast ID and network ID, it is still 30. So this is how you create subnets. Looking at the network bit, you'll first find subnet mask, then you can find the wildcard mask. Next thing you'll find the network ID. Network ID is the logical AND of the given IP and the subnet mask. Once you have the network ID, you can find the last IP of that network, broadcast ID, which is network ID plus the wildcard mask. This is not a logical AND operation here. It's normal decimal addition. So you just add the network ID plus the wildcard mask. You get the broadcast ID or the last IP of a network. And then the next network starts right after that IP.